it's my pleasure to welcome Rico Berner, our third speaker in our session. Rico is currently in Berlin, in Germany, and will talk about what adaptive neural networks teach us about power grids.
All right,
Rico, please go ahead.
Yeah, thank you very much. First of all, I would like to thank the organizers of this mini symposium and of course also of the conference to have this opportunity to give this talk. Yes, today I would like to talk about the relation between adaptive networks and power grids and what we can learn. This is in collaboration with Sergei Janczuk and Ecke Hatschel. In the beginning of my talk, I would of course like to let you know what we think are adaptive networks and what are power grid networks and what we are talking about. Then in the next step, I would like to convince you that actually the inertia term in power grid models is some kind of network adaptivity. And then in the last part of my talk, I would like to show you two examples or two applications of a new framework. And so let me just start with adaptive network part. So what is an adaptive network? Adaptive networks are, it's an ambitious paradigm in real world systems, and they appear in a lot of modeling approaches. When we think about in our group about adaptive networks, when we think about neuroscientific context, and of course, in this sense, about models of learning or memory or the development of neural circuits. And one example, one mechanism in neural circuits is so-called spike timing dependent plasticity. So in this mechanism, we consider maybe like, let's consider two neurons, neuron I, that's a postsynaptic neuron, and neuron J, which is a presynaptic neuron, and then we consider the synapse between them. And this synapse has a certain coupling strength, which scales the transmission from neuron J to neuron I. And then you consider, let's say, like regularly spiking neurons. So have a look at this time series. So you have time on the x-axis, and maybe it's consider the membrane potential of a neuron on the y-axis. And then you have a certain time, like certain but different spiking events for the different neurons. So here we have two different neurons. One is given by a dashed line and a solid line here. And if you look at this time, the spiking events, usually they're not at the same time. So there is a time interval and between them. And it has been shown or measured that according to this timing difference, the coupling weight can change. And this can be modeled by a simple rule. So the coupling weight gets an update to according to a rule. And if you look at the literature, there are plenty of different rules, but like the main features you can find is there are depression parts. So depending on the time intervals, there might be depression. So in decreasing of the coupling weight, or a potentiation of the coupling weight. And so this is what we actually look at if we talk about adaptive networks, because due to the spiking behavior of the neurons, the network structure given by the coupling weights is changing. And for the rest of this talk, we go one step back and consider a very simple model based on so-called phase oscillators. So let's consider a model, a network of phase oscillators where each phase oscillator is given by a phase between 0 and 2 pi. And the individual dynamics of each oscillator is just given by their natural frequency, omega I. Then we have a coupling between the oscillators given by a coupling function. We have coupling if between neurons or phase oscillators, depending whether this value of AI, the element of the adjacency matrix, is 0 or 1. And we have a coupling weight scaling this interaction. And on top of that, because we are talking about adaptive networks, we have also changes according to this dynamics of the phase oscillators of the dynamical variable, the coupling weight. And this is given by this equation quite generally, a linear filter term here in the beginning, and then we have something we call the adaptation function given by G. So this is our adaptive network setup. Okay, now we switch over to the power grids. The power grid network, for instance, have a look at the German ultra high power power grid network, where you can find in green squares net generators. So they produce power, like more power than they consume, or net consumers, so they consume more power than they produce. And this is actually the current power grid network of Germany. And what we want to have as a consumer, of course, we want to have a robust power supply, and this is achieved by like a synchronous solution of the dynamical system behind this power grid. Of course, as the provider, you would like to have cost-efficient power distribution, and also you would like nowadays to deal with renewable energies and go away from like a centralized system to a decentralized system, where you have like smaller power plants distributed on the map. Two basic equations which led us to the dynamics of such systems, or like the model of such systems, is the Swain equation, which models the individual generator or consumer just by a rotor. So we have a rotor, and the rotor angle is given by this delta here. We have certain momenta parameters, and we have a damping parameter, and we have some power influx and outflux given by, like, this is concerned with the mechanical power or the electrical power, and then you have also the power flow on the network. And if you put everything together, I'm not going to into detail here because you can read it. You can read everything in, for instance, Schmittendorf paper from 2014. If you write everything up, put it together, make some assumptions, you end up with a very nice equation, which is quite simple and can be written in this form. And this is again similar to a phase oscillator model. Instead of a phase, we have now the angle of a rotor, but it's also 0 to 2 pi. So it's a phase oscillator with inertia here. It's a second order differential equation for each phase on each node here. And we have a coupling function H, and we have a power, like a power for each oscillator, and we have a damping constant. All right, so this is what we are talking about if we look at power grids. And now the question is, can we relate these two models on phase oscillators? And the answer is yes, we can, but how? And this is what I am going to show you now. So on the left side, we see the power grids with inertia. So the phase oscillator with inertia, I just rewritten it in a system of first order differential equations. And here we have our adaptive neural networks. And now we have a look at this direction. So we want to show whether these two are somehow dynamical equivalent, and to have this direction on top, we first look at what if the coupling constant here, the coupling function is just 1. Fix it to 1. Then you see immediately that the first equation is quite similar to the first equation here. So on the left and the right side, it's quite similar. And in fact, if you introduce now what we call pseudo coupling weights and take op size to be the sum of all coupling weights, like the rows of all the pseudo coupling weights, and just redefine the coupling functions, then you end up in this kind of system. So what we can see is, just by rewriting this one, the left-hand side equation, so the power grid equation, and introducing new variables, we can rewrite it into adaptive networks. So this is quite nice, but the only thing which is left is, here on the left side we have two n differential equations. On the right hand side we have n squared plus n differential equations. So it's n squared minus n more differentiated. So we embed a lower dimensional system in a higher dimensional system. All right, so we have to prove also the back direction, so in which sense they are equivalent. And this can be done if we consider like this equation and rewrite it in a matrix-like form. So we introduce a matrix. It's an n in the lines, an n squared in the rows, dimensional matrix, B. The lines are just given by the lines of the adjacency matrix, and then they are stacked upon each other. Then we have the vector consisting of all the pseudo coupling weights. Then we can write this equation like this. And if we now define the image of this matrix as new coordinates, and we look at the coordinates of the kernel, so the zero set of this matrix, and rewrite this equation, we end up in this with this equation. So, and what we see is we have 1, 2, 3 lines. So 1, 2, 3 like main equations, and the third line does not depend on the first and the second line, but the first and the second line does not depend on the third line, which means in fact actually everything is governed, like the whole dynamic is governed by the first and the second equation, which makes it a 2n dimensional system again. So by embedding, what we can say is that we can embed the lower dimensional system into the higher dimensional system, and we can show that they are dynamically equivalent, which is very nice. So what we can say is that the power grid networks represented by the Kuramoto system with inertia is actually just a subset of adaptive networks. Okay, the same thing, just to let you know, can be done for a more complex dynamical system with voltage dynamics. Here the voltage dynamics becomes so-called, if you go back to the neuronal context, can be interpreted as meta-plasticity, so additional adaptivity of the adaptivity, so it's a meta-plasticity. What we develop is a unified framework in which we can now unify the power grid networks with inertia and the adaptive neuronal networks, where the angles are where the phases are, like the phase variable is either the angle of the mechanical rotor or the phase of the I-spiking neuron, where the psi I here on the left side is either the angular velocity of the ith rotor or the total synaptic weight, or if it's f is equal to 1, it's the total synaptic input. And the pseudo coupling weights, or the coupling weights, they are just the power flow from the rotor J to the rotor I, or the synaptic coupling weight between neuron J and I. All right. Everything was written up also in this paper. You can find it on the archive, and I will give you the reference also in the end of this talk. All right, so now we have a framework where you can go to the people dealing with adaptive networks and say, hey, we got tools from the power grid community, you can use them. Or the other way around, you go to the power grids guys and say, hey, we have tools from the adaptive people, you can use them. And this is what we want to trigger this now. So I just show you very briefly some 2 small applications. And the first thing is concerned with the multi-cluster states. We have done, just to let you know, we have done a lot of things on adaptive networks, which we now want to also use to analyze power grid networks. So it is concerned, for instance, with the multiplexing of adaptive networks, where we can show how we can stabilize and destabilize certain phase clusters. We've showed how the emergence of multi-cluster states in adaptive networks can be understood. We went over also to more complex network structures. So we had adaptive networks on non-locally coupled ring networks, where we analyzed the solitary states. which is a subset of multicluster states, or even just recently we developed a master stability function for a general, like a very general class of adaptive networks, which it's going to be on archive, like let's say soon, maybe tomorrow. All right, so regarding multicluster state, I just want to, because time is running, I would like to show you here two examples. So this is the equation we are looking at now. So this is a phase oscillator model with inertia. And here we see two different kinds of multicluster states. Multicluster states is, if we look at the average of the angular velocity, you see the grouping into groups of the same frequency. So they have the same collective frequency. And here you see the snapshots of the phases, so they are in phase, synchronous. And if you look at the pseudo-coupling weights, you can immediately see some kind of hierarchical structure, which has been also observed in adaptive networks. And on top, before it has not been found, but we found also some a very interesting, like from the dynamical point of view, very interesting phenomenon, which is called display cluster. This we have found by using tools from adaptive networks. So we developed tools in adaptive networks, and then we used them and to analyze the power grid networks, and found here we have two groups of the same frequency. And here one group has some kind of splay, so they're two twisted states. So the oscillators are distributed around the unit circle. And this is showing us that there's a presence of high multi-stability. And of course, if you're interested in a power grid, you don't want to have multi-cluster state, you want to have a synchronous state, but to understand the basin of attraction and the desynchronization of this synchronous solution, you have to understand the whole global, like the whole phase space. And of course, if there is a high multi-stability, you have to understand these multi-cluster states as well. So it's very necessary insight into the desynchronization also of the synchronous solution. And it has been shown that solitary states, in fact, which is a subclass of multi-cluster states, are very prominent in real power grids. So it's a paper by Hellman and collaborators, appeared in Nature Communications, and also Taher, Olmi, and Schöll, in Physical Review. They have shown that solitary states exist also in real power grid networks. The second thing we have done is to look at a very a phenomenon we know from the power grid networks and give an interpretation in the adaptive networks or for adaptive networks. This is what is called cascading line failures. So in power grids, cascading line failures is a line fails if the line capacity, so this is defined like this F is usually the line capacity, and if it goes beyond a certain value, a line fails. It has been shown in a work by Benjamin Schäfer, Mitau, Timmo, and Latorre, also Nature Communication, that actually also if there's initial perturbation in a very simple network, and there is a stable fixed point before the perturbation and after the perturbation, even though they are stable, there might be a cascading of line failures induced dynamically, because there are, after the perturbation, some lines that go beyond this value. And we have checked that whether this is also possible for adaptive networks. So what we have done here, use the very same model out of from this paper. So the very same network model, use very similar values, but put on top in adaptive networks where you have a Kuramoto type coupling here and some Hebbian-like. Hebbian means if the phase difference is very close to each other, so close to zero, there's an increase of the coupling weight. If they are far away from each other, then there's a decrease. We've shown that there's also some kind of cascading of line failures. So here you see the time series of now this is not the capacity of a line, so it's the localized synaptic input. So the capacity line can now be interpreted as the local synaptic input. And if it goes beyond a certain value, we can say this is it's failing, and this failing is induced or might be induced by, or it might be induced temporarily at least, due to something which is called the short-term depression. So there's another plasticity effect also in neurons, known in neurons. If there's a high active line, short-term depression can make a line deactivated. And with this, we just propose a very simple model to understand or to find a new effect from the interplay between spike time independent plasticity and short-term plasticity. All right, and yes, with this I come to my end. So what we've done is we bridged between the power grids and the adaptive networks by showing that they are somehow, like, the basic models are dynamically equivalent, and they are just a subclass, so the power grids are just a subclass of the adaptive networks. We've seen that we can find multiclusters and analyzed multicluster and solitary states with tools we developed for adaptive networks, and we proposed a simple model for temporal cascading of line failures also in the adaptive networks. So as I said, everything was written up in this manuscript. You can find it on the archive, and there's a lot of more theory we developed for adaptive networks you can find in the series of papers here. And I thank you for your attention, and happy to take your questions.
Thank you very much, Rico, for this excellent presentation. I will check the archives tomorrow if you have uploaded your paper that you have announced. So now we have time left for questions, and I see the first question in our question and answer forum. I assume, Rico, that you can also see it. You should be able to enter the question and answer forum, which is one of your menu items. It's right next to participants.
Might be the case. Yes, it is the case.
Okay, and now you should see it, but I still read it. Is f equal to 1 just one example or requirement for the transformation of the models? The phase model behavior can be quite interesting and underexplored in this limit. And this question comes from our colleague Istvan Kiss.
Yes, that's a very nice question. So yes, so for this transition between the power grid networks and the adaptive networks, this one is necessary. Yes, indeed. So we have to put it equals 1. This is why we're saying that the power grid networks, or the phase oscillator with inertia, a subset of all, or a subclass of the adaptive networks, of the class of adaptive networks. So this is just a subclass. Of course, if you put some more complicated coupling functions here, of course the dynamics will be different. But what we can see is that they are in the same class of models, and numerical studies shown that they are the same phenomena. And also you can use the same tools as we have shown in our manuscript. And it would be nice to trigger more like this collaboration between the communities now.
Okay, very good. For the moment, I cannot see an additional question in the forum. Let me ask you one. We want our power grids to be synchronized, correct?
Yes.
And you said that there's evidence for different solitary states and multi-cluster states in these networks. What would be more threatening to the stability of these networks from an engineering point of view?
Oh, that's a very good question. I guess, like, if you have it's like emergence of a solitary state might be handled by just very localized control rules. So I think in the desynchronization transition from like a synchronous to desynchronization, solitary states might be easier to control, I guess. But in total, of course, like what I wanted to highlight here is, even though there is a stable synchronous solution, there are a lot of different other solutions co-stable. And if you're not able to understand these solutions, then you cannot understand the basin of attraction of the stable of the synchronized solution, and cannot find like control mechanisms and stuff like that.
Okay, I understand. Thank you for your.
If there are no questions here, can I just chime in here, because this is the solitary paper was by us. I can't write a question in the Q&A because I'm a panelist, so I just have to jump in. First of all, thanks a lot for the talk, and just to clarify this, I think from my understanding of talking to engineers, all of these states would constitute a failure of the power grid. So it's really about understanding the presence of these states in phase space and that basin of attraction in phase space. And the most threatening one is always the one that sort of limits the basin the most. But just to clarify, these states cannot actually physically occur in power grids.
Yes, that's true.
If I may jump in and add that actually, I also think that the solitary states are more easily controllable. We have in fact published a paper, and Rico has cited it with Halgut Taher and Simona Olmi, where we showed that these solitary states can be quite easily controlled by time-delayed feedback. But multiclusters are, I think, more difficult to control.
And multiclusters also occur for a much wider range of parameters, I think. I mean, for us, the real insight in the solitaries was that the critical fact is that if you have alpha not equal to 0 in your language here, they become much more prominent, and they are underappreciated certainly in the engineering community as a threat. So
I agree.
Okay, very good. Thank you again.